Let's draw a vertical rectangle in there. So the blue curve, which is the blue curve? Which one of these equations? Yeah, it's negative because it has a negative slope. This one has a positive slope. This is x equals 1. And it says, so we're going to we'll do the washer method around the x-axis, and we'll do the shell method around the y-axis. So the washer method around a horizontal axis is the volume is equal to pi times the integral from a to b of capital R of x squared minus small r of x squared dx. So why don't you guys go ahead and come up with the, did we do that yesterday? I don't think we did. So go ahead and figure out what the outside radius is relative to the x-axis and what the inside radius is relative to the x-axis. Also the limits, we were talking about this. This x limit is not 3 or 3.5, it's somewhere in between. So to find this limit, we'll need to take the two linear equations, the first two linear equations, and solve for the value of x. So do that as well. So we know that the lower limit is going to be x equals 1. That's pretty obvious since the line x equals 1 defines that barrier. So congratulations to the forensic team, Kelly, and who else was Asia and Elias, and was there anybody else in here that I missed out? I don't think so. Huh? I got Kelly. Yeah. Did you hear about my comment? Yeah. That doesn't seem quite right. Let me try that again. Is it more than 2? It's right there. What's that? Oh, did I? Okay, because I know it's over 3 and 8/3 is not over 3, so I knew something was wrong. So let me just write this out. That still work? Did I? That's right. Did I? Oh, I used. Here? Oh, 0.5. Oh, what do you think it is? Should be 0.5. There's 2. There's. Oh wait, 2, 4, 6, 7. Actually, I think one of the equations is wrong. So let me look at this. Yeah, because this, yeah, one of the equations is wrong. This one's wrong. I think it has at least it has a y-intercept of 7, and I wrote 6 here. So if I change that to 7, let's see if I get a number that makes more sense. So this is 7. So that's -5. So yeah, that makes more sense. So that the problem was that I wrote this equation, or either I drew the graph wrong or I did the equation wrong. So I'm going to say the equation's wrong. So if you do that, you get x equals 10/3, which makes more sense. Okay, so the outside radius is going to be the blue curve, because that's the part of the rectangle that's furthest away from the x-axis. So blue curve is this one. So it's x minus x plus 7 squared minus 0.5x plus 2 squared, all times dx. Okay. Anybody have any questions about that one? Okay, so the next thing is to do the shell method around the y-axis. And remember, pretty much you can reuse everything that we've already used. The limits are going to be the same because we're rotating around the y-axis. P of x equals x. And instead of having this squared minus that squared, we just take the difference. So it's just going to be -x plus 7 minus 0.5x plus 2 dx. Okay, so that's that one. Let's go to the next one. So I guess it's this one here, right? So again, they're asking you which direction to do the rectangle. So we'll just take a vote here. Try to do your own thinking here, not looking to see what everybody else is doing. Hannah. Remember your. Do you think we should do a vertical or a horizontal rectangle? Don't look. Yes. So draw in a vertical rectangle. What's that?
A horizontal.
Yes, that's correct. Yeah. So Hannah says it's a horizontal, and I think she's saying that because you have the same. You only have one integral. Not that you can't do it the other way, but it's easier. I think you've got to in this case you've got to solve for the y value of the two intersections. So you'll need to do that. So you can solve for x and then plug x into the appropriate equation. But what we'll have is a shell method around the x-axis, and we'll have a washer method around the y-axis. So go ahead and do those things. So what I'll do is I'll put the equations up that you need to use for those. So we're doing a horizontal rectangle like that. That way the blue curve is always on the small side of the rectangle and the red curve's on the other one. And for the shell method, and they have to be a function of y because the rectangles are going to be stacked in this direction. So the shell method around the x-axis, and the equation for that is the volume is 2 pi times the integral from c to d of p of y times h of y times dy. And what we'll use the washer method around the y-axis. And the equation for that is pi times the integral from c to d of r of y squared minus r of y squared times dy. So you'll have to you'll need to solve these equations. So it's x equals some function of y. Since all this stuff is a function of y, and remember p of y equals y if you're going around the x-axis. And you'll need to find c is equal to 0. That's the one side of the triangle. The other value would be the y value corresponding to that point of intersection, which looks a little bit more than 4. And hopefully I did it right this time. So we got a new piece in our band. While you're working on this, I'm going to play you the piece. It's a fun piece to play. A little swinging. Do 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 do. Okay, so so I solved for x. Actually, that's x, not y, so I did that wrong. We still got to solve for y. So let me find the y value. So y equals 2x minus 1, so 2 times 13/5 minus 1, which is 26/5 minus 5/5, so that's 21/5. Okay, so I should change that. I'll fix that in a second here. 21/5. Let's double check the figure. So 21/5 should be a little bit over 4, which it is. Okay, so that looks reasonable. The blue curve is the one with the negative slope, and if you solve for y, you'll get x equals, well, you solve for x, you'll get x equals -1/3 plus 4 over here. And this equation, which is the red curve because it has a positive slope, you solve for y, you get 1/2 y plus 1/2. So that's the second one. So those are the two curves that we have to worry about. And we have the limits from 0 to 21/5. So for the shell method, we go integrate from 0 to 21/5. So that's our y limits. P of y is y. The more positive y curve is the blue curve, which has a negative slope. Then you subtract the red curve. So that's h of y, the difference between those two y values of x. And for the washer method, they have the same limits, and you still have the same two functions defining the boundary, except you square them and subtract them. And I'm missing a parenthesis here. So this is out. This is the outside radius because that's the one that's furthest away from the y-axis, and this is the inside radius because that's the closest one to the y-axis. Okay. What I'm going to do here is we have one more problem to do, but I'm going to do that on Monday. I want to start in section 4 just to do something different for a while. So let's open up section 4, which is the last section in this chapter. So we're almost ready for another test. No. Not quite. It probably won't be next week. It'll be the week after, probably Tuesday the week after. So the next section is arc length and surface of revolution. So the arc length is actually the length of the line. So what we've done so far is we found the area between two curves. So that was area. That was section 1. Then we looked at the volume, rotating areas around different axes. So what we're actually doing now is to figure out the length of a curve, which is completely, we've never done that before. We've done areas, we've done volumes, we've done the slope of lines, but we've never done the length of lines. And the second thing we're going to do is, instead of the flat area of a two-dimensional object, so we've been doing, what is the area of this object? That's the integral into the curve. What we're looking at is what is the surface area of revolution. So instead of the volume contained by a three-dimensional surface of revolution, it's going to be the surface area, which is still, it's still area. It's just it's wrapped around in 3 dimensions. Okay. So here is the kind of the problem that we're looking at. How do we find the length of the curve starting at a point A, x equals A, y equals f of A, and then we move along the curve until we get to some value x equals B over here, and the y value, corresponding y value. Now we've done that before in algebra and pre-calculus. We looked at lines, and the length of the line, we used the distance formula, which was just the Pythagorean theorem. But in this case, because the line is not straight, we can't use the Pythagorean theorem anymore. Of course, the easiest, the approximation to the length of this curve here is just to draw a straight line between the two, and that'll underestimate the length of the actual path along the curve. But we do start, even though I said it wasn't a straight line, we're actually going to use the formula for the distance on a straight line, because that's the whole thing about calculus. We started with the definition of slope for a straight line, and then we made the distance between the 2 points go to 0, and so instead of having an approximation for the slope, we had to get the exact slope, and we use a limiting process. For areas under a complicated shape, we just found the areas of rectangles, which are a simple calculation. So we're always taking a simple calculation and then using the limit process to look at more complicated situations. So the distance formula using the coordinates of the 2 points is the square root of y2 minus 1 y1 squared plus x2 minus x1 squared. And if you look at it, this is a right triangle. This is one side. This is the other. These are the two lengths of the two sides. So this squared plus that squared equals the hypotenuse squared. So the length, the straight line distance between these 2 points is the square root of this squared plus that squared. Okay. So I just said that. Okay, so here's the way we do it. We look at a small distance along the curve, and we call that delta S. So that's a small change or small increment along the curve. And we approximate that part of the curve as a straight line so that we can use the distance formula. And so the distance delta S here is going to be equal to delta x squared plus delta y squared. Instead of using x2 and x1 and y2 and y1, we use x sub I plus 1 and x sub I and y sub I plus 1 and y sub I. So that's just, we're looking at some arbitrary segment of that curve between points A and B. So that's using the I plus 1 subscript and the ith subscript to show the distance. What we're going to do is we're going to rewrite those as deltas, and ultimately we'll rewrite those as d's. So we'll change a delta into a d, so it'll be dx instead of delta x. But to make an approximation to the length along this arc, we just add up all these little small approximations. So to find the total length along the arc or along the curve, we sum from I equals 1 to n of all the individual little delta s sub i's. But delta s sub I is just the square root of delta x sub I squared plus delta y sub I squared. Okay. Now, what we can do now here is we can, what are we doing? We take the second term and we multiply and divide by delta x sub I. So we're just multiplying by 1, essentially. So we end up with delta x sub I squared plus delta x sub I squared times delta x sub I squared over delta y sub I squared over delta x sub I squared. But you can see we got the same term here, so we should be able to factor that out of the square root. So you can see that's what I've done there. So I've factored out delta x sub I because I have delta x sub I squared in here, so when you take it outside of the square root, it just becomes delta x sub I. So that's like our delta, when we did integrals in terms of areas, that ultimately became the dx part of the equation. And the summation here becomes the integral. So when we take the limit as n goes to infinity, we're going to be able to substitute this with the integral sign. We'll be able to substitute dx for this, And delta x sub I over delta y sub I divided by delta x sub I is just the derivative of the function. So this part we're going to be able to say is the derivative of the function. I'm not sure if that all happens in one fell swoop here, but we'll see what here. Yeah, pretty much. Yeah, there you go. So yeah, so those different steps by making the increment in the x and y directions infinitesimally small, we're going to call that means that we can replace delta x with dx. It means that we can take the limit as n goes to infinity and replace that with the integral, and the ratio of dx over dy over dx is the derivative. And so that's the equation. Okay. So to find the length of a curve between two values of x, a and b, you take the square root of 1 plus f prime of x squared times dx. And you can also do it in the y direction. So if you have a function that's easier to look at as a function of y instead of a function of x, you do the same thing, but you have to integrate between the two y values of the endpoints. So the equation doesn't look that bad for finding it. So let's just, I'm going to add a page here. Whoops, that's not what I wanted to do. Yes?
Those are F prime and G prime?
Yeah, G prime, well, yeah, G prime is just this version, but solved for y, for y. So you could, so they're different functions in some ways. They look different, just like the ones we just did in the previous problem. So let me add a page here. Keep that equation up. So let's say I wanted to find the length. So let's say here's a curve. Here's a axis, and we have y equals x squared. And I want to find the distance along this curve from x equals 0 to, let's say, x equals 3. And obviously this is not to scale because this would come over to 9. You know, an approximation would just be a straight line between these 2 points, which would be 3 squared plus 9 squared, take the square root. But of course, it actually doesn't go straight. It dips down a little bit. So for our particular equation, a is equal to 0. That's the x coordinate of the first point. And b is equal to 3. So all we need, what is f of x? F of x is equal to x squared. So f prime of x is what we need to plug into this equation is 2x. So the arc length is equal to the integral from 0 to 3 of the square root of 1 plus 2x quantity squared dx. Or s is equal to the integral from 0 to 3 of the square root of 1 plus 4x squared dx. So the integral doesn't look that bad, but it's not, we don't know how to solve that right now. We have to wait till chapter 8. So that's the problem with this section. It's not that hard to come up with the actual integral. The hard part is actually doing the integral. So it turns out that a lot of the equations that they choose for the lines are kind of weird equations, and the reason they use them is because when they substitute them into here, you have the tools to solve the integral. Because you think here, well, can I just say u is equal to 1 plus 4x squared, but then du would be 8x dx, but I don't have an x here, so I can't use substitution and make it into a polynomial. Now I could, let's just show you, if I did it the other way. So if I use this approach, so let me add a page here. So if I did, let me use a different color. So if I did it the other way, so it was S is equal to the integral from C to D of the square root of 1 plus g prime of y squared dy. What you'd have to do is take this equation, y equals x squared, and solve for x. So you get x equals plus or minus the square root of y, but because I'm on this side of the y-axis, it's just the plus the square root. So that's my function. I'm not sure if this is any easier. Still probably, you might still not be able to solve this one easier, but let's just show you how you set it up. So this would be y to the 1/2 power. So, no, actually it'll work out okay. If I just plugged it in here, but what I need to do is take the derivative. So g of y is y to the 1/2 power. So the derivative of that, g prime of y, would be equal to 1/2 y to the minus 1/2 power. So I take the exponent, reduce the exponent by 1. So then I plug that into here, and you get the integral from 0 to 9, because y goes from 0 to 9, and you'd have the square root of 1 plus 1/2 y to the minus 1/2 power squared dy. And if we square that thing, you'll end up with the integral from 0 to 9 of the square root of 1 plus, you end up with actually 1 over 4y, because this is the square root of y in the denominator, so when you square it, you get y in the denominator, and 1/2 squared is 1/4. So again, I don't know how to do that one either. I mean, or you don't know how to do that one either. So anyway, let's find an equation we actually can do. The point there is that some of the simplest functions that we've dealt with in finding areas underneath curves and finding derivatives, when you try to find the arc length, it's more complicated and possibly beyond what we know how to do. So let me see, yeah, so I tried that one, that didn't work. Okay, yeah, okay, so this is an example of one that does work, but you can see the function looks pretty crazy to start off with. So the equation is x to the 5th over 10 plus 1 over 6x cubed, and we want to find the arc length between x equals 1 and x equals 2. So when you take the derivative, the derivative of x to the 5th is 5x to the 4th, and the derivative of 1 over x cubed, which is x to the minus 3 power, is negative 3 times 1 over x to the 4th. So the second line is the derivative of the first thing. Then you can simplify it. 5 over 10 is a half, and 6 over 3 is a half. So that's the derivative. That's the square root of 1 plus f prime of x. So the f prime of x is this. And if you do the algebra inside there, so let's do that separately. So if I take 1 plus x to the 4th over 2 minus 1 over 2 x to the 4th squared, you'll get 1 plus x to the 8th. So x to the 4th squared is x to the 8th. 2 squared is 4. Then you have the inner and outer terms, so you'll have the x to the 4ths will cancel out, because you'll have this times that. And you'll have a half times a half. So there's a quarter, but there's 2 of those. So the result of multiplying the inner and the outer is negative 1/2. Okay, so let me just explain that if you're not getting it. So take that multiplied by negative 1 over 2x to the fourth. The x to the fourths cancel out, and you get negative 1/4. And because that happens twice, you add the two together and you get that. And then these multiplied together give you 1 over 4x to the 8th. And notice that this cancels, well, no, it doesn't cancel out. What you end up with is, so don't cancel that out. So you have 1 minus a half, so you'll end up with x to the 8th over 4 plus 1/2 plus 1 over 4x to the 8th. And then you can say that's x to the fourth over 2 what do I do here? It's a complete square, but it's not working. No, yeah, it works out. So if it's that plus 1 over 2x to the fourth squared. So if you see, you multiply these together, you get that. If you multiply these together, you get a quarter, and you get that twice, so you get positive a half, and you multiply these two together to get that. So ultimately, what happens is when you're calculating the integral, you integrate from 1 to 2, because that's what they asked for, and you get the square root of x to the fourth over 2 plus 1 over 2x to the fourth squared. And the square root of something squared is just that something. So ultimately you end up with the integral from 1 to 2 of x to the fourth over 2 plus 1 over 2x to the fourth dx. And lo and behold, I can integrate that. Okay? So it's a convoluted, it's like, I'm never going to be able to do that. Well, the good news for you is that I'm not going to make you do that. You will have some homework problems, but if you get stuck, you can watch the videos. So what we're going to do is we're going to, in general, use the online integrator to get our answers, so we don't have to do this every time. But if you look in the back of this section, you'll notice a lot of the functions that they're looking for the arc length for are much different than we've seen before. And it all comes down to the fact that simple functions sometimes become very difficult integrals when you're calculating arc length. Okay, so let's so that's arc length. Next thing in this section is surfaces of revolution. So I already kind of demonstrated that. You're basically taking a three-dimensional object. So you could imagine this as being solid, but I'm still looking for the surface area. So the surface area is a area, and I'm only worried about the surface. So the question is, how do you construct a three-dimensional surface from a two-dimensional figure? Well, all you do is you take, instead of taking an area and rotating around an axis, you take the arc length, you take the length of the segment, and you rotate it around the x-axis. I was trying to find something like here. So if I take this, and here's my axis, and I rotate it around the axis like that, and it really has zero width. In this case, it has to have some width because it wouldn't exist otherwise. But you can see how that would create by sweeping out this line through three-dimensional space. It's going to create a surface area. So that's what this figure shows us. And the area, the surface area of this little segment is just the circumference of the circle associated with this object times the length of the object. So 2 pi r is the circumference, and ds is the length of the segment, and so that's the area. So it's not a big stretch to understand where the formula comes from. So we get, instead of the integral from a to b of this thing, which gives us the arc length, what we do is we take 2 pi to give us our circumference. We still integrate between x equals a and x equals b, but we multiply by the radius of the distance from the x-axis to the curve, and we multiply that by the length of that little bit of segment. So this is the radius, and this is the ds part. And if we integrate all that stuff, we add up all those little line segments that rotate around to give us surface area. So the only thing that's different is we add 2 pi, which is easy because that's a constant, and we have to figure out what the radius is. And a lot of times the radius is the function. So the function, this is the function r of x, and the function are the same thing. So you take the derivative of the function inside here, and you multiply the whole thing by the function. And then you end up with an integral, which again tends to be a lot of times very complicated. So we're not going to worry about trying to do a bunch of complicated integrals. We're just going to use the online integrator to do that. But I'll give you an example. And again, you can do it. There's two. You can rotate it around the y-axis, just like we did with the volumes, or we can rotate it around the x-axis. But even if we rotate it around the x-axis, we can use either y as a function of x or x as a function of y, depending upon which is the easier one. That's the really complicated part. You've been trying to visualize how do I use the shell method and the this method and the washer method, and which way is this thing going, and in this case it's just about the same level or maybe more complexity. So again, I'm not going to ask you to figure that out. It took me a while to figure it out in my brain. So I'm going to kind of demonstrate some of those things to you. And so I'm just going to do this in a different. This is this one I want to do first. Let me just. Question is around the x-axis. Yeah. So I can do this around the x-axis or the y-axis. I think I'll do it around the x-axis because that's what we've been doing. So let's add a page here. So what I'm taking is this curve, which is a parabola upside down. I'm going to rotate it around the x-axis, and I'm looking for the surface area. I'm not rotating the area. I'm not rotating the area between the x-axis, the y-axis, and the curve around the x-axis. All I'm doing is rotating the curve, the line, around the x-axis. So it's just going to be like a piece of sheet metal that's stamped out, and you're asking, what's the area of that surface? So let me write out the equations for you. So we'll say area, the surface area, is 2 pi times the integral from a to b of r of x times the square root of 1 plus f prime of x quantity squared dx. Okay, well, with the easy parts, a is 0 because that's the x limit for this part, and the x limit for this part is 3. So those are my limits of integration. Now, this radius can either be the y coordinate, it can be y, or it can be the x representation of y. Okay, so we're going to do the x representation of y. So we're going to say r of x is equal to 9 minus x squared. That's the equation for this curve. F of x is also equal to 9 minus x squared. So in this equation, to calculate the surface area, we need r of x, which we have, and we need f prime of x. So we're going to take f prime of x, which is equal to negative 2x. So the surface area is just 2 pi times the integral from 0 to 3 of 9 minus x squared, which is the radius in terms of x, times the square root of 1 plus negative 2x squared dx. Again, that's not an easy integral. So what we're going to do is we're going to use an online integrator to give us the answer. So let's see what we got here. I must have listened to that about 10 times last night, reading the music. The hard part is the first trumpet and the second trumpet, at least for the first couple of lines, are different, doing different things. So you're trying to figure out what the heck. Okay, what am I doing here? Definite integral calculator. Okay, looks good. So I'm going to integrate from 0 to 3, and the function is, let me close this thing here. So it's 9 minus x squared times the square root of 1 plus, and I'm going ahead and square this out, so it'll be 4x squared. If you square the thing out, just make it easier. 4x squared. Okay, so the integral from 0 to 3 of 9 minus x squared times the square root of 1 plus 4x squared. Go. See, even it's having trouble. It's like Friday, don't do this to me. Oh, there it is. Okay, so the answer is 46.13. So that's the surface area, 41.63 whatever squared, something squared. So that's the way you would do it, using everything in terms of x. But you can do the same thing in terms of y. So what you do is you integrate 2 pi times the integral from c to d of r of y times the square root of 1 plus f prime, or we'll call it g prime, of y squared dx. So the limits, the y limits, go from, so c is equal to 0 and d is equal to 9. If you go back to the curve, you go from 0 to 9. R of y, in this case, is equal to y. So y is equal to 9 minus x squared. So in this case, I use y instead of 9 minus x squared. F of y is going to be equal to, you take this function, y equals 9 minus x squared, and you solve for x, and you'll get 9 minus y square root. So if I move this to the other side, it becomes positive. Move this to the other side, it becomes negative. Take the square root. It's the positive side. So that's f of y. So you get square root of 9 minus y. So you take the derivative of that with respect to y, and you'll get negative 1 divided by 2 times the square root of 9 minus y. So why is that? That's because you get 9 minus y to the 1/2. So you get 1/2 from here. You get a negative when you use the chain rule, and then you get 9 minus y to the minus 1/2. So that's f prime of y. And I'm doing this quickly because I want to show you the result, so you'll be impressed that this thing actually works. So what I'm going to do is do this integral. So it'll be negative 1 over 2 the square root of 9 minus y squared dy. So r of y is y. F g prime of of y is, I should have used g here, sorry, is that. So I should be able to plug that in and get the same answer. So we'll see if it works or not. So what I'm going to do is I'm going to change the limit to 9. I'm going to put in y here, which I think, well, I'll put in x, but it doesn't matter what it's just a variable. So let me, so what I'll have here is -1 divided by 2 times the square root of 9 minus y, and this whole thing is squared here. So this thing is squared. Oh, I don't square it twice. What happened there? Okay, delete that. Okay. So I think that's right, except I need to put x in there, not y. Okay. So I got the integral from 0 to 9 of x times the square root of 1 plus -1 over 2, the square root of 9 minus x, quantity squared, the whole thing square root times dx, and I say go, drum roll, and if I did everything right, I should get 41 point whatever the answer was. Give it another difficult one, I guess. 46.13. Woohoo! Look at that. Isn't that impressive? So, so the whole I just did that because I think it's amazing. I mean, you look at it. We have different limits. We have completely different equations, even though we really don't because we just solved for the other variable. But the fact they turn out to be exactly the same, Evan, isn't that impressive? That would impress you. Maybe nobody else, but maybe Margaret. I don't know. Maybe Seth. Right? But anyway, so we'll continue on this. So.